The previous weeks, we overviewed the KerasCV library and trained the YOLO V8 model on a custom object detection dataset. Today, we'll be training the segmentation model DeepLabv3 on a custom dataset using KerasCV. Hey there, welcome to LearnOpenCV. We are using the satellite images of Waterbodies dataset. A model trained on this dataset can be used for surveying and drone imaging. There are a total of 2800 images in the dataset along with their accompanying segmentation mask. These images, however, aren't binary masks, so we will have to process them. To follow along with me, open the blog post link from the description, then click on the download code banner, fill your details and hit enter. You'll receive an email with the notebook link, download it and let's get started. Let's take this dataset to Google Colab and train our DeepLabv3 model. As usual, we get a V100 GPU. That's the best Colab has to offer right now. We'll first set up our environment, which starts with installing KerasCV, and then we import it and other modules. We need OS and glob for path operations, requests and zip file to download and extract the dataset, and data class to easily configure our dataset and model. Then random for random number generation and shuffling our data, NumPy and OpenCV to display the images, and we will use TensorFlow framework and KerasCV to train and run inference on DeepLabv3 model. We'll be using Matplotlib to plot multiple images. Next, we will define the seed to reproduce the results. Every run is different and produces a unique output, but initializing a seed value will ensure the same results are always generated. Next, we will download and extract the dataset and then prep it. We use request.get to get the zipped dataset file and then use zip file to extract the downloaded file. Next, we use data class to define the data and training configurations, also known as the hyperparameters. For example, the input image to the model will be 256 x 256, batch size will be 16, number of classes are 2, which are 0 for background and 1 for the water body. A brightness factor and contrast factor for the augmentations are also defined here. These hyperparameters will stay consistent throughout the training pipeline. Similarly, we also set the training hyperparameters like the model name, number of epochs, the learning rate of the optimizer, the checkpoint directory to save the model, and the logging directory to save the training logs and graphs. We will modify the number of epochs to 3 to quickly train our model. If these concepts are difficult for you to grasp, you should check out OpenCV University's free TensorFlow and Keras bootcamp. Go to openCV.org/university/free courses to know more. Moving on, we are prepping the dataset for training, which includes handling large amounts of data, performing transformations on it, and managing multiple data formats. Here we are getting the paths to the image and the masks, zipping them and shuffling them together so the image and mask mapping is not lost. The shuffling helps us avoid training biases. Combine them into TF dataset. So now, we can split our dataset into train and test set in a 95:5 ratio. The training set has 2700 images and the validation set has 140 images. But the dataset split consists of image paths, and we cannot train the model on image paths. So next, we will read the images. The function readImageMask does just that. It inputs the image path, a boolean flag whether the image is masked or not, and the input image size, which we have defined to be 256. First, let's understand the else statement. We first decode the input image and then set the image shape to have 3 channels. Next, we resize the image using bicubic interpolation method, and finally, we clip the pixel values between the range 0 and 255 and cast the image to float32 data type. Now, if this were a mask, we also have to process it. So, if mask, decode the input image and set the shape to have 1 channel and resize it. Now, if the pixel values are above 200, it will be set to 1 and 0 otherwise. The function then returns the image as a TF tensor. Now the function load data calls the above function readImageMask and returns the image and mask as a dictionary. Finally, we create the train and validation datasets. UnpackageInputs is a utility function that inputs the dictionary images and returns them as a tuple. Now let's take a break and visualize the data. For visualizing the ground truths, we will set colors to the class IDs. Black for the background and light blue for the water body. For the following functions, we will use NumPy and OpenCV to overlay the mask. First, we convert the single channel binary mask to colorful images. Mask pixel value 0 stays black, but mask pixel value 1 becomes light blue. Then this function overlays the colorful segmentation map on top of the RGB image. Finally, this function plots the input image, the ground truth, and the overlaid image. Here are some of the dataset images. Next up, we will use KerasCV to augment the images. Augmentations are necessary to introduce variability to the dataset, which helps the model generalize better. Always make sure the augmentations you do are meaningful. In this case, random flipping, brightness, and contrast. Then we map the augmentations to the training dataset only and create the final train and validation dataset, which will be used for model training. Let's have a look at the augmented images. We are done with the dataset preparation. Now on to model initialization. We initialize ResNet v2 feature extractor with ImageNet weights and then initialize the DeepLabv3 Plus model for 2 classes and ResNet 50 v2 backbone. Here is the model summary. It has a total of 39 million parameters. To evaluate the model, we will monitor the IOU. Check this blog post to know more about it. With this function, we calculate the mean IOU between the ground truth and the model predicted output. We will also define 2 callbacks: TensorBoard for logging the performance metric graphs and model checkpoint to save the fine-tuned weights. Finally, on to training the model. Compile the model with Adam Optimizer, sparse categorical cross-entropy as the loss function, and the metrics to be evaluated. In this case, accuracy and the mean IOU that we defined above. Call model.fit to train the model, pass the train dataset, validation dataset, number of epochs, and the callbacks to be used. Now sit back, relax, and watch your model train. During every epoch, the model will calculate the training loss, training accuracy, and training mean IOU values, and after every epoch, the model will evaluate the validation loss, validation accuracy, and validation mean IOU. We have only trained the model for 3 epochs, but you can see the loss is decreasing and the accuracy and MIOU is increasing. Now let's evaluate the model. The results won't be splendid, but if you would have trained the model longer, we are bound to get better results. To load the best weights saved by the callback, use model.loadWeights. To evaluate the model on a dataset, use model.evaluate and pass the dataset as the argument. And to run inference on a single image, use model.predict. This function will predict a few images and plot them. So that's all about training KerasCV DeepLabv3 Plus model on Waterbodies dataset. If you like this video, why don't you check out how to train an object detection model using KerasCV on a custom dataset or other videos in the KerasCV playlist. Do comment on what you would like to see next and don't forget to subscribe. Thanks for watching. Until next time.